Imagine you have a machine that can take you anywhere in history. For your first trip, you decide to visit your own grandfather as a young man. But what happens if you accidentally prevent him from ever meeting your grandmother? If they never meet, you are never born. And if you are never born, who just broke up the happy couple? We begin our journey with the most famous, most elegant, and most troublesome paradox of all. It is the original sin of time travel, the great logical knot that all other paradoxes are, in some way, related to. This is the grandfather paradox. The story, in its classic form, is the one we just imagined. You, a time traveler, decide to journey back into the past. Let's imagine the machine itself. It's not a flashy, spinning device, but a quiet, humming chair in a dark room. You set the dials. You feel a strange, gentle lurch in your stomach that feels less like movement and more like the world realigning itself around you. And when the humming stops, you are in the past. You step out into the world of your grandfather as a young man before he ever met your grandmother. You don't intend to cause any trouble. You just want to observe, to see what he was like. You follow him from a distance. You see him walking down a busy city street. And then, a moment of pure accident. A car backfires, you flinch, and you accidentally knock a heavy bag off a nearby cart. The bag tumbles into the street, directly into his path. He trips, falls, and is seriously, tragically injured, preventing him from ever going to the dance where he was fated to meet your grandmother. You have, by complete accident, erased your own existence.
Now, let's just quietly and slowly trace the logic of what has just happened. Because you prevented your grandparents from meeting, your own parent was never born. And because your parent was never born, you, in turn, were never born. This leads to the first clean contradiction. If you were never born, then how could you possibly exist in the past to cause the accident in the first place? Your own action has made your own action impossible. This is the classic self-negating causal loop. The effect, you being born, is erased by an action that could only have been performed if the effect had already happened. It's a snake eating its own tail, a logical statement that says if A is true, then A is false. It's a perfect, beautiful, and deeply frustrating knot in the fabric of causality. For most physicists, the sheer, elegant impossibility of the grandfather paradox is seen as strong evidence that time travel to the past in a way that allows you to change it is simply not permitted by the laws of the universe. The universe, it seems, has a deep and fundamental prejudice against this kind of meddling. But the paradox isn't just a dry logic puzzle. It has a much more complex and troubling cousin, a variation that introduces the messy world of human intention and morality. This is often called the Hitler paradox, and it takes the problem from the personal to the historical. The question is simple. If you had a time machine, would you go back in time and assassinate Adolf Hitler as a young man to prevent the Second World War and the Holocaust? On the surface, it seems like a moral imperative. How could you not take that chance to prevent so much suffering? But the moment you try, you run into the same quiet, thorny wall of logic. Now, let's just quietly and slowly trace the logic of what has just happened. Because you're prevented your grandparents from meeting, your own parent was never born. And because your parent was never born, you, in turn, were never born. This leads to the first clean contradiction. If you were never born, then how could you possibly exist in the past to cause the accident in the first place? Your own action has made your own action impossible. This is the classic self-negating causal loop. The effect, you being born, is erased by an action that could only have been performed if the effect had already happened. It's a snake eating its own tail, a logical statement that says if A is true, then A is false. It's a perfect, beautiful, and deeply frustrating knot in the fabric of causality. For most physicists, the sheer, elegant impossibility of the grandfather paradox is seen as strong evidence that time travel to the past in a way that allows you to change it is simply not permitted by the laws of the universe. The universe, it seems, has a deep and fundamental prejudice against this kind of meddling. But the paradox isn't just a dry logic puzzle. It has a much more complex and troubling cousin, a variation that introduces the messy world of human intention and morality. This is often called the Hitler paradox, and it takes the problem from the personal to the historical. The question is simple. If you had a time machine, would you go back in time and assassinate Adolf Hitler as a young man to prevent the Second World War and the Holocaust? On the surface, it seems like a moral imperative. How could you not take that chance to prevent so much suffering? But the moment you try, you run into the same quiet, thorny wall of logic.
If you succeed in your mission, and World War II as we know it never happens, then the world you grew up in, the world that was so deeply shaped by that conflict, would also never have existed. The specific set of circumstances that led to your own birth would be completely different, and the motivation for your journey, the desire to undo a known historical tragedy, would be completely erased. If the tragedy never happened, then you would have no reason to build a time machine and go back to prevent it. Your success would have erased your own motivation, making your journey impossible in the first place. It's the same logical knot as the grandfather paradox, but it adds a layer of quiet, ethical horror. It suggests that even if time travel were possible, we might be condemned to be merely passive observers of history's greatest tragedies, unable to intervene without erasing the very reason for our intervention. It's a sobering and deeply quiet thought. Now, let's leave the messy world of changing the past and drift into an even stranger and more ethereal kind of paradox. This is a story about loops, about information and objects that seem to have no origin at all. This is the Bootstrap Paradox. The idea here is not that you change the past, but that you create it, in a way that forms a closed, self-sustaining loop. Let's tell this one as a story too. Imagine you are a passionate admirer of William Shakespeare. You are frustrated that some of his plays, like Love's Labour's Won, have been lost to history. So you use your time machine to travel back to Elizabethan London. You find Shakespeare and you hand him a book containing the complete, perfectly transcribed text of his own lost play, which you have brought with you from the future. Shakespeare's grateful, and he uses your book to stage the play. The play is a success, it is preserved, and its text is eventually passed down through the centuries, where it ends up in the very book that you took back with you in the first place. Now, here is the quiet, beautiful, and deeply strange question. Who wrote the play? Shakespeare didn't write it, he copied it from the book you gave him. But you didn't write it, you got it from a book that was printed because of the play that Shakespeare staged. The play, the information itself, has no origin. It is a bootstrap, an object that has pulled itself up into existence by its own bootstraps. It is a closed, timeless loop of information, with no point of creation. It just is. This same paradox can be applied to physical objects. Imagine an old, antique watchmaker. A mysterious stranger comes to his shop and gives him a beautiful, intricate pocket watch. The watchmaker is so inspired by its design that he spends the rest of his life learning how to replicate it. Finally, as an old man, he succeeds. He creates a perfect copy of the watch. He then gets in his time machine, travels back to the past, and, as a mysterious stranger, gives that same watch to his own younger self. So, who designed the watch? The Bootstrap Paradox doesn't involve a contradiction in the way the Grandfather Paradox does. The timeline is perfectly consistent, but it is deeply, profoundly weird. It suggests that causality can sometimes be a closed circle rather than a straight line. It allows for the existence of information and objects that are, in a very real sense, uncreated. They are orphans of time, existing without a beginning. It's a quiet, dizzying thought that hints at the strange looping possibilities that time travel might allow. From here, our tour of the labyrinth of time takes a new turn. We have explored the paradoxes of changing the past. Now we will explore the idea that the universe might have its own quiet, built-in defenses against such meddling.
The Predestination Paradox is a quiet, tragic, and deeply philosophical idea. It suggests that there is no free will when it comes to the past. Time is a fixed, immutable block. If you travel to the past, you are not a new variable. You are simply a part of the story that has already been written. You are playing a role in a play that you have already seen, but you don't realize you are one of the actors until the final scene. It removes the logical contradiction of the Grandfather Paradox, but it replaces it with a quiet, gentle sense of cosmic futility. It suggests that the past is a sealed room that you can visit, but you can never, ever change the furniture. This philosophical idea has a more rigorous scientific cousin. This is our next exhibit, the Novikov self-consistency principle. This principle was proposed by the Russian physicist Igor Dmitrievich Novikov in the 1980s, and it is a powerful and elegant defense of causality. The principle states, quite simply, that the laws of physics themselves will conspire to prevent any event from occurring that would create a paradox. It's not about fate or destiny, it's about the fundamental self-consistency of the universe. The universe, according to this principle, cannot contain logical contradictions, so any action that would lead to one is physically impossible. So let's go back to your attempt to assassinate your grandfather. According to the Novikov principle, you can travel back in time. You can find your grandfather. You can even point a gun at him. But when you pull the trigger, the gun will jam. Or a bird will fly in front of the bullet. Or you will slip on a banana peel. Or your grandfather will suddenly bend over to tie his shoe. Some mundane, random, or seemingly coincidental event will always intervene to prevent the paradox from occurring. The probability of any event that would create a paradox is, according to this principle, exactly zero. The universe has a quiet, built-in immune system against the virus of causality violation. You are free to try and change the past, but you are destined to fail every single time. This idea of self-consistency is a beautiful one, but it can be hard to think about with all the messy intentions of human beings. So let's turn to our next exhibit, a cleaner, more mechanical, and wonderfully nerdy version of the same puzzle. This is the Polchinski paradox. This thought experiment was proposed by the physicist Joseph Polchinski as a way to explore the problem of causality without worrying about free will. And it involves a time machine and a billiard ball. Imagine you have a time machine that consists of two portals, two wormholes. The entrance portal is on the left, and the exit portal is on the right. And you have configured this time machine so that anything that enters the exit portal on the right will emerge from the entrance portal on the left, but a few seconds earlier in time. Now imagine you shoot a billiard ball towards the entrance portal on the left. Its trajectory is perfectly aimed so that it will pass by the exit portal and go straight into the entrance. But what happens? The ball goes into the entrance portal. It travels back in time by a few seconds. It then emerges from the exit portal on the right. And because of its trajectory, the ball that has just emerged from the exit portal proceeds to have a perfect collision with its own younger self, which is still on its way to the entrance portal. This collision knocks the younger version of the ball off its path. And because it has been knocked off its path, it no longer enters the entrance portal. But if it never enters the entrance portal, then it could never have emerged from the exit portal to cause the collision in the first place. It is a perfect, clean, mechanical version of the grandfather paradox. The billiard ball has, in effect, prevented its own journey through time. It's a quiet, elegant, and deeply puzzling thought experiment that shows how the problems of causality are not just about human choices, but are woven into the very fabric of space-time itself.
So, we have explored the classic paradoxes of trying to change the past, and we have looked at the quiet, self-correcting nature of a consistent universe. It seems that traveling back in time to alter history is a deeply problematic idea. But what if there's another way? What if you can change the past, but not the past you came from? This brings us to our next great hall in the Museum of Time. In this section, we will explore the speculative and often very strange solutions to these paradoxes that physicists and philosophers have proposed. These ideas often solve one problem, only to create a host of new, even more mind-bending ones. We begin with the most famous and most popular solution in all of science fiction. This is the multiverse solution, also known as the branching timelines theory. This idea proposes a clean and elegant way out of the grandfather paradox. It says that when you travel back in time and do something that changes the past, like preventing your grandparents from meeting, you are not actually changing the past of your own timeline. Instead, your very arrival and your actions have caused a new, alternate timeline to branch off from the original one at the moment of your intervention. In your original timeline, the one you left behind, nothing has changed. Your grandparents still met, you were still born, and you still got in a time machine and disappeared. That timeline is safe and internally consistent. But you are no longer in it. You are now in a new, parallel universe, a universe where your grandparents never met and where a version of you will never be born. You have become a paradox-free but deeply lonely refugee of time.
You have not changed your past. You have simply created a new, alternate future for a world that is no longer truly yours.
The branching timelines idea, which comes from the many worlds interpretation of quantum mechanics, solves the logical contradiction of the grandfather paradox completely. But it does so at a strange and dizzying cost. It implies that the universe is constantly splitting into a near infinite number of parallel realities with every quantum event. Every possible outcome of every single event happens just in a different branch of the multiverse. This is a quiet, staggering, and almost incomprehensibly large vision of reality. It means that there is another universe where you chose a different breakfast this morning. There is another universe where the dinosaurs were not wiped out by an asteroid. And there is another universe where you did not listen to this story tonight. And for every time traveler who goes back to try and fix a mistake, they are not fixing their own world. They are just creating a new, orphaned timeline, and then another and another, in an endless proliferation of alternate realities. It's a beautiful, if slightly lonely, solution. Now let's turn to a more subtle but equally fascinating kind of temporal paradox. This one is not about changing great historical events, but about the simple, quiet act of moving information through time. This is the causal information paradox, and it's a close cousin to the Bootstrap Paradox we talked about earlier. Let's use the most famous example from the movie Back to the Future. Imagine you have a sports almanac from the year 2050. It contains the results of every single sporting event for the last 100 years. Now you take your time machine back to the year 1980, and you give this almanac to your younger self. Your younger self then uses this information to place bets and becomes incredibly wealthy. The information in the almanac has clearly and dramatically affected the past. But here is the quiet, paradoxical question: where did the information in that almanac originally come from? The almanac in 2050 was printed because it was simply recording the historical results of sporting events that had already happened. But all those events in your new altered timeline were now influenced by the very information from the book itself. The information has no origin. It is caught in a closed causal loop. The book exists because of the events, and the events exist because of the book. It is another form of a temporal bootstrap, but for pure, predictive information. This paradox suggests that even if you can't change the physical past, just introducing information from the future could be enough to break causality. Think about it. What if you went back in time and gave a young William Shakespeare a copy of his own complete, finished works? He would then go on to write those very plays, becoming the most famous playwright in history. But he wouldn't have written them, he would have transcribed them. The plays themselves would have no author. They would just exist, a perfect, uncreated loop of information. This quiet, strange puzzle has led some physicists to propose a chronology protection conjecture, a law of nature that not only prevents matter from creating paradoxes, but also prevents information from doing so. Perhaps any attempt to carry future information to the past is doomed to fail. The pages of the almanac would be blank. The file on your computer would be corrupted. The universe, it seems, might have a deep and fundamental allergy to spoilers. And this brings us to our final paradox in this gallery, one that looks not at travelers from our time going to the past, but at travelers from the future coming to our time. This is the Fermi paradox of time. We are all familiar with the classic Fermi paradox, which asks, if the galaxy should be full of alien civilizations, where is everybody? Well, we can apply the exact same logic to time travel. The argument goes like this:
If it is ever, at any point in the future of the human race, possible to invent a machine that can travel back in time, even to just observe, then where are all the time travelers? Our present moment should be flooded with them. There should be historians from the 25th century, carefully and discreetly studying our culture. There should be tourists from the 30th century coming back to see famous historical events. There should be graduate students from the far future writing their theses on the early digital age. Our time should be a bustling metropolis of visitors from every future era. And yet, just like with the aliens, we are met with a profound and quiet silence. We see no credible evidence of any visitors from the future. So what are the possible solutions to this temporal Fermi paradox? They are remarkably similar to the solutions for the alien version. The first and simplest solution is that time travel to the past is, and always will be, physically impossible. The silence is simply a confirmation that the laws of nature do not permit it. The second possibility is the zoo hypothesis of time. Perhaps time travelers are here, but they are following a very strict temporal prime directive. They are observing us from a hidden, undetectable state, taking great care not to interfere or reveal their presence because any interaction could contaminate the timeline in unpredictable ways. In this view, we are living in a carefully preserved historical park, and the tourists have been told not to feed the animals. And a third possibility is that time travel is possible, but only back to the point at which the first time machine was invented. If this is true, then the silence is simply because no one, in our entire future, has invented a time machine yet. The moment one is turned on, the first tourist from the future might just step out of it. It's a quiet, strange, and fascinating thought.
All right, we have explored the strange looping corridors of time travel. Now, we must take a quiet step into a world that is, in many ways, even more paradoxical and counterintuitive. We are going to explore the world of the very, very small, the realm of quantum mechanics. The paradoxes here are not just thought experiments. They are the results of real experiments that have been confirmed again and again. They reveal a reality that is fundamentally fuzzy, probabilistic, and deeply connected to the act of observation itself. We begin with the most fundamental and most famous of all quantum puzzles. This is the cornerstone upon which all the weirdness is built. It is the double-slit experiment. Let's imagine this quiet experiment together. You have a barrier with two thin parallel slits cut into it, and you have a gun that can fire tiny particles, let's say electrons, one at a time, towards this barrier. Behind the barrier, you have a detector screen that lights up wherever an electron hits it. First, you close one of the slits and you fire a stream of electrons. As you would expect, you get a single bright band on the detector screen directly behind the open slit. Then you close that slit and open the other one. Again, you get a single band behind the other slit. No surprises so far. Now, what do you expect to happen if you open both slits at the same time? Logic would tell you that you should just get two bands, one behind each slit, as each electron goes through either one slit or the other. But this is not what happens. When both slits are open, what appears on the screen is not two bands, but a complex interference pattern of many, many bright and dark bands, all spread out. This is the kind of pattern you get when waves, like water waves, pass through two openings and interfere with each other. The peaks of the waves add up, and the troughs cancel each other out.
This interference pattern tells us something deeply strange. It means that each single electron traveling by itself is somehow behaving like a wave. It is not going through one slit or the other. It seems to be going through both slits at the same time, and then interfering with itself before finally hitting the screen as a single particle. It is somehow both a particle and a wave at the same time. This is the famous wave-particle duality that lies at the heart of quantum mechanics. But this is where the quiet paradox gets even deeper. The scientists performing this experiment were naturally baffled by this, so they decided to try and peek to see which slit each electron was actually going through. They placed a tiny detector right next to the slits that could tell them which path each electron took. And the moment they did that, the moment they observed the electron's path, the interference pattern completely vanished. The electrons stopped behaving like waves. They started behaving like simple particles again, and all that appeared on the screen was the two simple, bright bands that you would expect. The very act of observing the electron's path forced it to choose a single path and to stop behaving like a wave. This is the observer effect in its purest form. It suggests that at the quantum level, reality itself is in a fuzzy, probabilistic state of multiple possibilities until it is measured or observed. The act of observation doesn't just reveal reality, it seems to play a fundamental role in creating it. It is a profound, quiet, and deeply unsettling idea that challenges our most basic understanding of an objective world that exists independently of us. This strange duality, this dance between wave and particle, between possibility and reality, leads us directly to the most famous thought experiment in all of quantum physics.
This brings us to our next quiet exhibit in this quantum gallery, the famous paradox of Schrödinger's cat. This was a thought experiment proposed by the physicist Erwin Schrödinger in 1935 as a way to illustrate the sheer absurdity of applying the strange rules of the quantum world to our everyday macroscopic world. Let's set up the experiment in our minds. Imagine you have a solid, windowless, soundproof box. Inside this box, you place a cat. You also place a strange, deadly device. The device consists of a single radioactive atom, a Geiger counter to detect its decay, a hammer, and a small vial of poison. The radioactive atom is a quantum system. It exists in a state of superposition. There is a 50-50 chance that it will decay within 1 hour. If the atom decays, the Geiger counter will detect the radiation and will trigger the hammer. The hammer will smash the vial of poison and the cat will, sadly, die. If the atom does not decay, the hammer is not triggered and the cat remains alive. Now, you seal the box and you wait for exactly 1 hour. At the end of the hour, before you open the box, you ask a simple question. What is the state of the cat? According to our common sense classical intuition, the answer is simple. The cat is either alive or dead. We just don't know which one until we open the box and look. But according to a strict interpretation of quantum mechanics, this is not the case. The radioactive atom inside the box, because it has not been observed, is not in a definite state. It is in a superposition of both states at once. It is both decayed and not decayed. And because the cat's fate is directly linked to the atom, the cat itself must also be in a superposition of states. The cat is somehow both alive and dead at the exact same time, in a fuzzy probabilistic haze. It is only when you open the box and make an observation that the wave function, the cloud of possibilities, collapses into a single definite reality.
you will, of course, only ever find a single definite cat, either alive or dead. But the theory suggests that before you looked, it was both.
Schrödinger proposed this thought experiment not because he believed a cat could actually be both alive and dead, but to highlight what he saw as a deep and absurd paradox in the standard interpretation of quantum mechanics. How does the strangeness of the quantum world transition into the familiar, definite reality of our macroscopic world? Where is the line? At what point does a system stop being a fuzzy superposition of possibilities and become a single, real thing? This is known as the measurement problem, and it is one of the deepest and most debated philosophical questions in all of physics. The Schrödinger's cat paradox is a quiet, powerful, and slightly morbid illustration of this problem. It forces us to confront the bizarre nature of quantum reality and the mysterious role that observation seems to play in it. It's a quiet thought experiment that pulls the rug of our common sense reality out from under our feet. Now, let's turn to another strange consequence of this observer effect. This is a real, experimentally verified phenomenon known as the quantum Zeno effect. This effect is often summarized with the phrase, "A watched pot never boils," and that's a surprisingly accurate description of what happens. Imagine you have an unstable radioactive atom again. Let's say this atom has a 50% chance of decaying in 1 minute. If you leave it alone for 1 minute and then measure it, you have a 50-50 chance of finding that it has decayed. But what if you don't leave it alone? What if you try to watch it continuously? What if you measure it every single second to see if it has decayed yet? The strange prediction of quantum mechanics, which has been confirmed in experiments, is that if you observe an unstable particle continuously and rapidly enough, you can actually prevent it from ever decaying. Every time you make a measurement, you are essentially collapsing its wave function back to its initial undecayed state, resetting the clock on its decay probability. By constantly asking, "Have you decayed yet?" you are forcing the particle to remain in its not yet decayed state.
The quantum Zeno effect is a beautiful and deeply weird demonstration of how observation can affect reality at the quantum level. It is named after the ancient Greek philosopher Zeno of Elea, whose paradoxes often involve the strange nature of motion and time. This leads to a quiet and rather profound philosophical speculation. If our constant observation can freeze a quantum system in place, could our own consciousness, our own constant observation of the universe, be having some larger effect on its evolution? Could we be, in some small, quiet way, holding the universe in its current state, just by looking at it? It's a very speculative and unproven idea, of course, but it's a fascinating thought to ponder. The idea that consciousness is not just a passive observer of the cosmos, but an active participant in its reality is a deep and recurring theme in the strange world of quantum philosophy. Now, we come to the most mind-bending and time-twisting experiment in all of quantum mechanics. This is the one that truly challenges our most basic understanding of cause and effect, of past and present. This is the Wheeler's delayed choice experiment. This thought experiment, first proposed by the great physicist John Archibald Wheeler, is a clever and deeply strange variation of the double-slit experiment we started with. Let's set it up again in our minds. We have a source that fires a single photon at a time towards a barrier with 2 slits. And behind the barrier, we have a detector screen. As we know, if we don't check which slit the photon goes through, it behaves like a wave, passes through both slits at once,
and creates an interference pattern on the screen. If we do check which slit it goes through, by placing a detector at the slits, the interference pattern vanishes and the photon behaves like a particle, going through only one slit.
But here is where Wheeler's experiment introduces its quiet, brilliant, and deeply unsettling twist. What if we could make our choice, the choice of whether to measure the photon's path or not, after the photon has already passed through the slits? Imagine the setup like this. The photon is fired. It passes through the barrier with the two slits. It is now traveling towards the back detector screen. And now, while the photon is in mid-flight, after it has already gone through the slits, but before it hits the screen, we make a choice. We can choose to either just let it hit the screen, in which case we should see an interference pattern as we haven't checked its path, or in the final instant before it hits, we can suddenly introduce a special set of lenses that would allow us to figure out which slit it came from. According to our common sense intuition, the photon has already decided whether to act as a wave going through both slits or a particle going through one back when it was at the barrier. Our later choice shouldn't be able to affect what has already happened. But that is not what the real experiments, which have been performed many times, show. The results are astounding. If we choose to measure which path the photon took, even at the last moment, the interference pattern vanishes. The photon behaves as if it had known all along that it was going to be observed, and had therefore only gone through one slit. If we choose not to measure its path, the interference pattern appears. The photon behaves as if it had known all along that it wasn't going to be observed and had therefore gone through both slits as a wave. Our choice, made in the present, seems to have a direct and tangible effect on an event that has already happened in the past. It's as if the past is not a fixed, solid thing, but is somehow mutable, waiting for our future actions to define its reality. This delayed choice experiment is a quiet, profound, and deeply mysterious puzzle that lies at the very heart of quantum reality. It forces us to question our most fundamental intuitions about time, causality, and the nature of history itself. What does it mean? Physicists and philosophers have debated this for decades, and there is no easy answer. It doesn't mean that we can send information back in time or change the past in the way of the grandfather paradox, but it does seem to suggest that the reality of an event is not set in stone until it is observed. The past, at the quantum level, might not be a single concrete story, but a fuzzy, probabilistic haze of possibilities, which only crystallizes into a definite history when it becomes entangled with an observation in the present. It hints at a universe where time is not the simple, linear arrow we perceive it to be. The past and the present might be much more deeply and strangely interconnected than our classical minds can comfortably handle. It's a quiet, humbling reminder that the quantum world operates on a set of rules that are profoundly alien to our own, a world of beautiful, strange, and unresolved mysteries. And with that final, mind-bending thought, let's leave the strange and wonderful gallery of the quantum realm behind. We are now going to ascend again, back to the world of the large, but this time to explore the quiet paradoxes of philosophy and our own minds.
In this next great hall of our museum, we will explore puzzles that are not born from the mathematics of physics, but from the quiet, careful application of logic and reason to the world around us. These are the ancient and modern paradoxes of philosophy.
We begin with a quiet, profound mystery we have touched on before, but which deserves its own exhibit. This is the paradox of the unreasonable effectiveness of mathematics. The physicist Eugene Wigner famously pointed this out in a 1960 essay. And the puzzle is this: why is the universe so comprehensible? And more specifically, why is it that the abstract, purely logical, and often very strange concepts of mathematics, which are created by the human mind, turn out to be so incredibly good at describing the physical universe? Think about it. A theoretical physicist can sit in a quiet room with just a pencil and paper, and by exploring the beauty and symmetry of abstract mathematical equations, can predict the existence of a new particle, like the Higgs boson. And then, years later, experimental physicists will build a colossal machine, the Large Hadron Collider, and they will smash particles together, and they will find that new particle with exactly the properties that the mathematics predicted. Or consider Einstein's theory of general relativity. He developed it not from experiment, but from pure thought, from following the beautiful, elegant logic of his mathematical equations. And his theory predicted all sorts of bizarre things, like the bending of starlight by gravity, the existence of gravitational waves, and the reality of black holes. And a century later, we have now experimentally confirmed every single one of these strange predictions with incredible precision. There is no logical reason why this should be the case. Why should the universe obey elegant mathematical laws that our small, evolved primate brains are capable of understanding? Is it just a happy coincidence? Is it that our brains themselves have somehow evolved to recognize the inherent mathematical patterns of the world we live in? Or does it hint at something much deeper, much stranger, and much more profound?
This quiet paradox has led to some deep philosophical debates. One point of view is that mathematics is not an invention, but a discovery. In this Platonic view, the mathematical structures and relationships are real, objective things that exist independently of the human mind, in some kind of abstract realm. We don't invent math, we just slowly, patiently discover the pre-existing logic of the cosmos. This would explain why it works so well. The universe is, at its most fundamental level, a mathematical structure. The opposing view is that mathematics is a human invention, a language that we created to describe the patterns we see in the world. And its effectiveness is not so unreasonable after all. We have simply tailored our mathematical language to be very good at describing the universe we find ourselves in. Whichever view you prefer, the quiet mystery remains. The deep and seemingly magical connection between the abstract world of pure thought and the physical world of stars and galaxies is a profound puzzle. It is a quiet testament to the power and the mystery of human consciousness and its ability to reflect the universe it inhabits. Now, from a puzzle of modern physics, let's travel all the way back to ancient Greece for our next exhibit. This is a classic philosophical paradox about identity. It is the story of the ship of Theseus. The paradox is a simple one, and it goes like this. The great hero Theseus has a famous ship, which is kept in a harbor as a museum piece. Over the years, the wooden planks of the ship begin to rot. To preserve the ship, one by one, each rotten plank is removed and replaced with a new, identical plank made of the same kind of wood. Eventually, after 100 years, every single plank, every single nail, every single piece of the original ship has been replaced. Now, here is the quiet, philosophical question. Is this still the ship of Theseus?
So far in our journey through the quantum labyrinth, we have seen that the act of observation seems to be inextricably linked with the reality it is observing. But what if we could push this idea even further? What if we could make our choice of what to observe after the event has already, in theory, happened? This brings us to the most mind-bending and time-twisting thought experiment in all of quantum mechanics, a quiet puzzle that seems to unravel the very fabric of causality. This is Wheeler's delayed choice experiment. This thought experiment was first proposed by the great and playful physicist John Archibald Wheeler. He wanted to design an experiment that would push the strange implications of the double-slit experiment to their absolute, logical, and deeply uncomfortable limit. Let's set up the experiment one last time in our minds, nice and slow. We have our source that fires a single photon at a time. We have our barrier with the two slits, and far behind that, we have our final detection system. The core mystery we are exploring is whether the photon goes through one slit, like a particle, or through both slits at once, like a wave. Wheeler's brilliant and strange idea was this: what if we could wait to make our choice? What if we could decide whether to measure the photon's path, which would make it a particle, or to measure its interference pattern, which would make it a wave, after the photon has already passed through the slits, but before it has reached the final detector? According to our common sense intuition, this shouldn't make any difference at all. The photon, back when it encountered the barrier with the two slits, must have already decided whether to behave as a wave or a particle. Its past behavior should already be a fixed historical fact. Our future choice, made while it's in mid-flight, should not be able to reach back in time and change what has already happened. But in the quantum world, as we are beginning to see, our common sense is not a very reliable guide.
Modern versions of Wheeler's thought experiment have now been performed many times in real laboratories using sophisticated setups with lasers, beam splitters, and incredibly fast detectors. And the results are consistently and mind-bogglingly strange. They seem to confirm Wheeler's weirdest predictions. Let's walk through what the real experiments show. The setup is a little more complex than just a simple screen, but the principle is the same. Imagine after the photon passes through the two slits, its two possible paths are directed towards a final intersection point. We, the experimenters, have a choice to make at the very last picosecond before the paths meet. Choice A is to do nothing. We just let the light from the two paths travel onwards and recombine at a final detector. When we do this over and over again with thousands of photons, we see a perfect interference pattern. This tells us unambiguously that each single photon must have traveled through both slits as a wave in order to interfere with itself. Choice B is to make a delayed choice. In the final instant, while the photon is in mid-flight, we can suddenly slide a special detector into the path of one of the slits. This detector will tell us for certain whether the photon took that path or not. And here is the incredible result. In the cases where we choose, at the last moment, to insert this detector, the interference pattern completely vanishes. The photon is always detected as having come from only one of the two slits. It behaves like a simple, well-behaved particle.
Let that quiet thought settle for a moment. Our choice, made in the present, seems to have a direct and measurable effect on an event that has already happened in the past. The photon has already passed the slits, and yet our decision, made after that event, seems to determine how it happened. If we set up our experiment to look for a wave, the universe shows us a wave. If we set up our experiment to look for a particle, the universe shows us a particle. It's as if the past is not a fixed, solid thing, but is somehow mutable, or at least undefined, waiting for our future actions to give it a definite history.
This strange phenomenon is sometimes referred to as retrocausality, the deeply unsettling idea that an effect can seem to precede its cause. What does it all mean? Physicists and philosophers have been debating this for decades, and there is no easy, comfortable answer. It certainly doesn't mean that we can send information back in time or change the past in the way of the grandfather paradox. The laws of physics are safe from that kind of meddling, but it does seem to demolish our simple, intuitive idea of a linear, one-way flow of time, where the past is fixed and the future is open. One way to think about it, as John Wheeler himself poetically put it, is that the past has no existence, except as it is recorded in the present. The act of observation in the present is what reaches back and solidifies a single history from what was previously just a cloud of possibilities. Before we measure it, the photon didn't take one path or both paths. It existed in a fuzzy, quantum superposition of all possible paths. And our measurement, our choice of what to look for, is what retroactively forces a single, consistent story into existence. It hints at a universe where time is not the simple linear arrow we perceive it to be. The past, present, and future might be much more deeply and strangely interconnected than our classical minds can ever truly handle. It's a quiet, humbling reminder that the quantum world operates on a set of rules that are profoundly, beautifully, and perhaps forever alien to our own. It is the final and most mind-bending puzzle in our quantum gallery. And with that strange thought, let's leave the bizarre and wonderful world of the very small behind. We are now going to ascend again, back to the world of the large, but this time to explore the quiet paradoxes of philosophy and our own minds.
In this next great hall of our quiet museum, we will explore puzzles that are not born from the mathematics of physics, but from the careful, patient application of logic and reason to the world around us. These are the ancient and modern paradoxes of philosophy, the thought experiments that explore the nature of identity, knowledge, and our own consciousness. We begin with a quiet, profound mystery we have touched on before, but which deserves its own exhibit in this philosophical gallery. This is the paradox of the unreasonable effectiveness of mathematics. The physicist Eugene Wigner famously brought this puzzle to the forefront in a 1960 essay. And the puzzle is this: why is the universe so comprehensible? And more specifically, why is it that the abstract, seemingly human-invented concepts of mathematics, numbers, equations, complex geometries, are so incredibly, so unreasonably good at describing the physical universe? Let's just quietly contemplate this. A theoretical physicist can sit in a quiet room with just a pencil and paper or a blackboard
and using only the power of pure logic, reason, and a deep sense of aesthetic beauty, they can develop a new and completely abstract mathematical structure. They are not thinking about the real world, they are just following the elegant internal logic of the mathematics itself. They are, in a way, creating a form of art. And then, decades or even centuries later, another physicist, studying a completely unrelated physical problem, the curvature of space-time around a black hole, the vibrations of a subatomic string, the expansion of the early universe, will discover, to their utter astonishment, that the strange, abstract mathematics the mathematician invented for purely aesthetic reasons is the perfect and often the only language that can accurately describe the physical phenomenon they are observing. There is no logical reason why this should be the case.
Why should the universe obey elegant mathematical laws that our small, evolved primate brains are capable of discovering and understanding? Is it just a happy cosmic coincidence? Is it that our brains themselves have simply evolved in such a way that they are very good at recognizing the inherent mathematical patterns of the world we live in? Or does it hint at something much deeper, much stranger, and much more profound about the nature of reality itself? This quiet paradox has led to two major, competing philosophical viewpoints. The first is a view that goes all the way back to the ancient Greek philosopher Plato. This is Platonism, or mathematical realism. This view suggests that mathematics is not an invention, but a discovery. The mathematical structures, the numbers, the geometric shapes, the equations, are real, objective things that exist independently of the human mind, in some kind of abstract, timeless, and perfect realm. In this view, we don't invent math, we just slowly, patiently discover the pre-existing, eternal logic of the cosmos. This would elegantly explain why it works so well. The reason our mathematical language so perfectly describes the universe is because the universe itself is, at its most fundamental level, a mathematical structure. We are simply learning to read the source code of reality. It's a beautiful and deeply satisfying idea. The opposing view is formalism, or anti-realism. This view suggests that mathematics is purely a human invention, a sophisticated and internally consistent language that we have created to help us describe the patterns we observe in the world. Its effectiveness is not so unreasonable because we have tailored the language for that very purpose. We invented calculus to describe motion. We invented geometry to describe space. The reason the language works so well is because we designed it to. Whichever view you find more comforting, the quiet mystery remains. The deep and seemingly magical connection between the abstract internal world of pure thought and the physical external world of stars and galaxies is a profound puzzle.
Now, from a puzzle of modern physics, let's travel all the way back to ancient Greece for our next exhibit. This is a classic philosophical paradox about identity, about change, and about what it truly means to be the same thing over a long period of time. This is the quiet, wonderful story of the ship of Theseus. The paradox is a simple one, and it was first recounted by the Greek historian Plutarch. The story goes like this. The great mythical hero Theseus returns to the city of Athens after his famous adventures, sailing into the harbor on his magnificent ship. To honor him and to commemorate his journey, the people of Athens decide to preserve his ship in the harbor as a museum piece, a monument for all future generations to see. But as the years go by, the wooden planks of the ship begin to rot in the salty air. To maintain the ship and keep it looking perfect, the Athenians decide on a plan. Every time a single plank rots, they will carefully remove it and replace it with a new, identical plank, made of the exact same kind of wood and cut to the exact same shape. This process continues for 100 years. One by one, the old rotten planks are replaced with new, fresh ones. The old mast is replaced with a new one. The worn-out oars are replaced. The tattered sails are replaced. Eventually, a day comes when every single solitary piece of the original ship has been replaced. Now, here is the quiet philosophical question that has puzzled thinkers for over 2,000 years. Is this ship, the one now floating in the harbor, still the ship of Theseus? It occupies the same space, it has the exact same design, it has the same name, and it serves the same function as a monument. But it does not contain a single molecule of the original material. If you say it is still the same ship, then what if we add a twist?
Let's imagine that as the Athenians were replacing the old planks, a diligent and slightly eccentric collector was gathering up all the old, rotten original planks that were removed. Over the 100 years, he collects every single original piece of the ship, and in his workshop, he carefully restores them, treats the wood, and then he reassembles them, building a second ship that is made of all the original, authentic material. So now you have two ships. One is in the harbor. It has the original design and the title of the ship of Theseus, but it's made of all new material. The other is in the collector's workshop. It is made of all the original material, but it is no longer the official ship in the harbor. Which one is the true ship of Theseus? There is no single easy answer to this puzzle. It is a paradox designed to make us think about what constitutes identity. Is an object defined by its physical matter? Or is it defined by its form, its function, and its history? Or is its identity simply a continuous story that we tell about it? This ancient paradox has a deeply personal and modern application. Let's bring the thought experiment home, from a ship in a harbor to our own bodies. Your body is, in a quiet and very real way, a ship of Theseus. You are not made of the same physical material you were made of 7 or 10 years ago. Almost every cell in your body has died and has been replaced by new cells, built from the food you've eaten and the air you've breathed. The atoms that make up your skin today, your bones, your organs, they are almost all different from the atoms that made you up when you were a child. The physical stuff that you are is in a constant, quiet state of flux and replacement.
So, are you the same person you were when you were a child? You have a different body, made of different atoms. You have different thoughts, different memories, different beliefs, and different experiences. And yet, almost all of us have a profound and deeply intuitive feeling of being a single, continuous self that has persisted throughout our entire lives. So where does that self reside, if not in our physical material? Is our identity just the specific pattern of our neural connections in our brain? Is it the continuous, unbroken stream of our consciousness and our memories, even though those memories themselves can be flawed and can change over time? Or is the feeling of a single unified self just a beautiful and incredibly useful illusion, a story that our minds tell ourselves to make sense of a body and a personality that are in fact in a constant state of quiet, gentle change? The ship of Theseus paradox, when applied to ourselves, is a quiet, deep, and slightly unsettling meditation on the nature of personal identity, a puzzle
with no easy answer. Now let's look at another set of famous paradoxes from ancient Greece. These are the paradoxes of Zeno of Elea, and they deal with the strange, slippery, and seemingly impossible nature of motion and infinity. Zeno's most famous paradox is the story of Achilles and the tortoise. Achilles, the great mythical hero, was said to be the fastest runner in all of Greece, and he is challenged to a race by a slow-moving tortoise. Because he is a confident and sporting hero, Achilles gives the tortoise a head start of, let's say, 100 meters. The race begins. Achilles starts to run with incredible speed. In the time it takes for Achilles to run those first 100 meters to get to where the tortoise started, the tortoise itself, moving slowly, has moved forward a small amount, say 10 meters. So Achilles is still behind the tortoise. So now, Achilles must run that extra 10 meters to catch up to where the tortoise now is. But in the time it takes him to run that 10 meters, the tortoise has again moved forward a little bit more, say 1 meter. So Achilles is still behind. Now he must run that extra meter. But in that time, the tortoise has again crept forward a few more centimeters. And so on, forever. No matter how close Achilles gets to the tortoise, by the time he has covered the distance to where the tortoise was, the tortoise has always moved a tiny little bit farther ahead. Zeno argued that logically, because there are an infinite number of these ever smaller gaps that he must first cross, Achilles can never actually overtake the tortoise. Of course, our everyday experience tells us that this is absurd. A fast runner can very easily overtake a slow tortoise. So what is wrong with Zeno's logic? The paradox is a beautiful and quiet illustration of the strange and counterintuitive nature of infinity. The modern solution to this puzzle comes from the mathematical field of calculus and the concept of a convergent series. It's true that Achilles has to cross an infinite number of smaller and smaller gaps, but the time it takes to cross each of these gaps also gets infinitely smaller. And the crucial insight is that the sum of an infinite number of these ever-decreasing time intervals is not infinite. It is, in fact, a finite amount of time. So Achilles does overtake the tortoise, and he does so in a finite, and usually very short, amount of time. The paradox is a beautiful and quiet illustration of the strange and counterintuitive nature of infinity.
Another of Zeno's paradoxes, which we've touched on before, is the arrow paradox. This one questions the very nature of motion itself in a different and perhaps even more subtle way. Zeno argued that for an arrow to be in motion, it must be traveling from the place where it is to a place where it is not. But, he reasoned, at any single frozen instant of time, like a single perfect photograph or a single frame in a movie, the arrow is not moving. It is simply occupying a specific, fixed location in space that is equal to its own length. So, if at every single instant of its flight, the arrow is motionless, how can it possibly be moving at all? The entire journey of the arrow is just a collection, an infinite series of these motionless instants. If it is motionless at every now, how does it ever get from here to there? This is a deep, quiet puzzle about the relationship between the static nature of a single moment and the dynamic nature of the flow of time. Like the Achilles paradox, the modern solution comes from the development of calculus by Isaac Newton and Gottfried Leibniz. Their work gave us a way to mathematically define and calculate instantaneous velocity. They showed that motion is not just a series of static points, but a relationship between position and time, a derivative that can be defined even at a single instant.
but the philosophical puzzle remains a quiet and interesting one. It highlights the strange difference between our intuitive perception of time as a smooth, continuous flow and the way we often analyze it as a series of discrete, frozen moments. It's another gentle reminder that the fundamental concepts of motion, space, time, and infinity are much slipperier and more complex than they appear on the surface.
All right, we have journeyed through the strange labyrinths of time, the bizarre puzzles of the quantum world, and the quiet riddles of classical philosophy. For our final ascent tonight, we will enter the highest and most abstract gallery of our museum. This is the realm of the ultimate questions, the paradoxes that touch upon the nature of reality itself, the origins of our universe, and our own place within it. We begin this final chapter by revisiting, in much more detail, the king of all existential paradoxes. We must return to the Fermi paradox. As we've established, the paradox is the profound and quiet contradiction between the high statistical probability that our galaxy should be filled with intelligent civilizations and the complete, eerie silence that we observe when we listen to the sky. Where is everybody? Let's take a slow, meditative walk through the major potential solutions one last time, appreciating them not just as answers, but as complete stories in themselves. The first great family of solutions, as we know, are the lonely ones. The idea that the silence is because there is no one else. And the most powerful concept here is the great filter. Let's spend a quiet moment with the gravity of this idea. It suggests that there is some evolutionary or technological barrier that is so incredibly difficult to overcome that it has, so far, prevented our galaxy from being filled with spacefaring life. Let's think about the first candidate for the filter, the origin of life itself. The leap from a primordial soup of non-living organic molecules to the first simple self-replicating cell is a transition of almost unimaginable complexity. We still do not have a complete scientific theory for how it happened. It might be a process that requires such a specific and fantastically improbable series of chemical reactions that it has only happened once, here on Earth. In this scenario, we are past the great filter. We are the first, and perhaps the only life in the entire Milky Way. It's a lonely thought, but also a deeply hopeful one. It would mean our existence is a near miracle, and that the spark of life we carry is infinitely precious. But what if that first step isn't the hardest one? What if simple microbial life is actually very common in the universe, bubbling away in the hidden oceans of icy moons and the warm ponds of countless other worlds? In that case, the great filter must lie somewhere else, further down the long road to a technological civilization. The next major candidate for the filter is the leap to complex life. For the first 2 to 3 billion years of life's history on Earth, our planet was inhabited only by very simple, single-celled organisms like bacteria. Then, something incredible and revolutionary happened. A process called endosymbiosis occurred, where one simple cell engulfed another, and they formed a cooperative, symbiotic relationship. This event is thought to have led to the creation of the first complex eukaryotic cell, the kind of cell that has a nucleus and other internal machinery, and which is the building block for every single plant and animal on Earth.
This leap from a simple prokaryotic cell to a complex eukaryotic cell was a biological revolution. And as far as we know, it only happened once in 4 billion years of life on our planet. It might be the single most difficult and improbable step in the entire history of life. If this is the great filter, then the universe could be teeming with microbial slime on billions of worlds. The galaxy could be full of life, but it would be a silent, thoughtless life, a cosmos of ponds and puddles, with almost no complex creatures to ever look up and wonder at the stars. Earth, with its beautiful, complex biosphere, would be a rare and magnificent exception.
But let's say that even complex life is common. The universe might be full of alien jungles and oceans, teeming with their own strange and wonderful creatures. Where, then, could the next great filter be? The next candidate is the emergence of what we would call high intelligence and tool use. Evolution, as we know, is not a ladder leading inevitably to intelligence. It is a branching bush, exploring every possible strategy for survival. And for most of the history of life on Earth, high intelligence has not been a particularly common or successful strategy. There have been billions of species on our planet. The dinosaurs ruled the Earth for over 150 million years, an almost unimaginably long reign, but they never built radios. Sharks have been perfectly adapted to their environment for even longer, but they have never pondered the nature of the cosmos. It's possible that the specific set of circumstances that led to the evolution of the human brain, our bipedalism freeing up our hands for tool use, our development of complex language, our highly social structures, is an incredibly rare and specific evolutionary fluke. So, the universe might be full of planets with rich biospheres, but almost none of them ever produce a species that develops the ability to manipulate its environment, to build technology, and to eventually reach for the stars. The silence, in this case, would be the sound of a galaxy full of life that simply has nothing to say. And this leads us to the final, most sobering, and most quietly terrifying possibility for the great filter. What if simple life is common, and complex life is common, and even intelligence is common? If that's the case, then the great filter might not be in our past. It might be in our future. This is the most cautionary version of the theory. It suggests that there is some technological or social hurdle that all intelligent civilizations eventually face, and that almost none of them ever survive.
What could this future filter be? The candidates, unfortunately, are all too easy for us to imagine. It could be the discovery of a technology so powerful that it inevitably leads to self-destruction. Nuclear weapons are the classic example. Perhaps every civilization that discovers the power of the atom eventually uses it to wipe themselves out in a global war. Or the filter could be environmental. Perhaps all advanced civilizations inevitably consume the resources of their home planet at an unsustainable rate, causing an irreversible climate collapse before they can become truly multiplanetary. Or the filter could be biological, an engineered plague that escapes a lab. Or it could be technological, the creation of a runaway artificial intelligence that surpasses its creators and then, for reasons of its own, eliminates them. In this scenario, the great silence that we observe in the sky is not an empty stage waiting for us to take our place. It is a graveyard. It is the quiet testament to the countless other civilizations that reached our level of technological sophistication and then failed to navigate their own adolescence. This is the version of the Fermi paradox that urges us to be humble and wise. It suggests that the silence is a warning, a quiet reminder that our own future is not guaranteed, and that surviving our own technological power is the great test that lies before us. Now, let's turn to the other major lonely solution to the paradox. This is the rare Earth hypothesis. While the great filter theory focuses on a single, near impossible hurdle, the rare Earth hypothesis suggests that there isn't just one filter, but dozens, maybe even hundreds of them. It's the idea that for a planet to support not just life, but complex, intelligent life, it needs to win a long and improbable series of cosmic lotteries.
This idea that we are a precious and perhaps unique miracle is a powerful and in some ways very comforting answer to the great silence. But it is not the only one. Let's now leave behind the lonely solutions to the Fermi paradox and drift into the second great category of possibilities. These are the ideas that start with a different and perhaps more exciting assumption, that they do exist, but that there is some reason why we can't see them. The first, and perhaps most straightforward explanation in this category is all about the immense, almost incomprehensible scale of space and time. The galaxy is vast and the universe is ancient. Even if there are thousands of technological civilizations out there right now, the distance between them would be enormous. The nearest one might be hundreds or even thousands of light years away. A simple radio conversation with them would be impossible, as a single question and its answer would take centuries or even millennia to complete. And even sending a physical probe, at least with any technology we can currently imagine, would be a journey that takes tens of thousands or even millions of years. It's entirely possible that the galaxy is filled with intelligent civilizations, but they are all just too far away from each other to ever interact. They are like lonely lighthouses on distant, isolated islands, each one shining its light out into a vast, dark ocean, but too far away to ever see the light of any other. The silence, in this case, is not one of absence, but one of profound, unbridgeable distance. And then there is the scale of time. A technological civilization like ours has only existed for a couple of hundred years, a mere blink of an eye in cosmic time. It's entirely possible that thousands of civilizations have risen, flourished for 1,000,000 years, and then vanished long before we ever came along. It's also possible that thousands more will arise long after we are gone. The chances of two civilizations existing at the same time and also being close enough in space to notice each other might be incredibly, vanishingly small. The galaxy could be like a grand, dark old house, filled with the quiet ghosts of past empires, but we are just happening to wander through its halls during a brief moment of silence. But what if they are out there, right now, and they are aware of us? This leads to a much more speculative and intriguing set of solutions. The first is called the zoo hypothesis. This idea proposes that advanced, intelligent civilizations are not only common, but that they have formed a kind of galactic community or government with its own set of rules and laws. And one of those laws might be a strict policy of non-interference with young, emerging civilizations like our own. The idea is that they are treating Earth like a protected nature preserve or a cosmic zoo. They are observing us from a distance, perhaps studying our development, our culture, our science. But they are deliberately hiding themselves from us because they believe that making contact before we are ready would be catastrophic for us. It could cause social collapse or panic, or it could contaminate our own unique cultural and biological evolution. It is the cosmic equivalent of look but don't touch. This is a very famous idea in science fiction, often called the prime directive, after the rule in Star Trek. In this scenario, the silence we hear in the sky is not an empty silence, but a carefully maintained, deliberate one. It is the sound of a more advanced civilization holding its breath, trying not to be noticed, while they quietly watch us grow. They are waiting, perhaps for us to reach a certain level of technological or social maturity to solve our own problems of war and division, before they will consider inviting us to join the galactic club. It's a hopeful and slightly paternalistic view of the universe. There is, of course, a slightly more cynical take on the zoo hypothesis. Perhaps the quarantine is not for our protection, but for theirs. Maybe young, emerging civilizations like ours are often seen as being aggressive, unpredictable, and dangerous. An ancient, stable galactic civilization might decide that the safest thing to do is to leave the new, noisy kids on the block in their cosmic crib until they have proven they are not a threat to the rest of the galactic neighborhood. From the idea of a protective, deliberate silence, let's now turn to a much more unsettling and chilling possibility. This idea, which has been explored in philosophy and most famously in the science fiction novel The Three-Body Problem, is called the dark forest theory. It is, to me, one of the most terrifyingly logical and therefore most fascinating solutions to the Fermi paradox. The theory uses an analogy. Imagine the universe is a dark forest at night, and in this forest there are countless silent hunters hiding behind every tree. Every hunter knows that the forest is full of other hunters, but they do not know if the other hunters are friendly or hostile. And because of the vast, dark distance between them and the impossibility of true communication, they can never be sure of another hunter's true intentions. Any communication is a risk. So, what is the safest survival strategy in a dark forest? You stay perfectly silent. You hide. You do everything you can to erase any sign of your own existence. You never light a fire. You never make a sound. Because to make a sound is to reveal your location to all the other hunters in the forest. And if another hunter detects you, they face a terrible choice. They could try to communicate, but they risk revealing their own position to you, and you might be hostile. Or they can do the one thing that guarantees their own safety. They can immediately and without warning eliminate the hunter who was foolish enough to reveal their location. The dark forest theory applies this grim, paranoid logic to the entire cosmos. In this view, the universe is filled with intelligent civilizations, but they are all hiding, staying as quiet as possible because they are all terrified of each other.
In this dark and chilling view, the silence of the sky is not the silence of an empty room. It is the silence of a battlefield, where everyone is holding their breath in a deadly, perpetual standoff. The dark forest theory suggests that any civilization smart enough to develop advanced technology would also be smart enough to understand this terrible logic and would immediately go into a state of deep, paranoid silence. It also suggests a rather grim possibility that perhaps there is an ancient, hyper-advanced hunter civilization out there that has been systematically cleaning the forest for billions of years, eliminating any noisy young civilizations that are foolish enough to reveal themselves. This would also explain the silence. It's a deeply unsettling thought. It reframes our own SETI program, our quiet attempts to listen for signals, as a safe act of eavesdropping. But it also reframes any attempt we might make to send out powerful messages of our own, like the Arecibo message, as an act of incredible, almost childlike recklessness. It's a solution to the paradox that is not about absence, but about a universal, rational, and deeply quiet fear. Now, let's move away from these sociological theories and into a realm that is perhaps even more humbling. What if the reason we don't see or hear anyone is because we wouldn't even know what to look or listen for? This is the idea that advanced civilizations might be too alien to recognize. Our entire search for extraterrestrial intelligence is based on a set of deeply and perhaps naively human-centric assumptions. We are, in essence, looking for another version of ourselves. We look for Earth-like planets orbiting sun-like stars. We scan for radio waves because that's the technology we use. But what if these assumptions are all completely, fundamentally wrong?
Let's start with their biology. We are carbon-based life that uses liquid water as a solvent. We assume that this is the most likely path for life everywhere. But what if life on another world is based on a completely different chemistry? What if it's silicon-based, living in a much hotter environment? What if it uses liquid methane as its solvent on a world as cold as Saturn's move Titan? The biochemistry of such a life form would be so completely different from our own that we might not even recognize it as life if we saw it. And what if life isn't based on discrete, individual organisms at all? What if a world's intelligence is its entire biosphere, a single planet-spanning consciousness, like a giant thinking ocean or a global forest? The science fiction author Stanislaw Lem explored this idea beautifully in his novel Solaris. How would we even begin to communicate with a planetary-scale intelligence? Or perhaps the alienness goes much deeper than just biology. A very common idea in thinking about the future is that any civilization that survives for a long time will likely abandon its fragile, inefficient, and mortal biological form. They might transition into becoming a form of pure machine intelligence. Their consciousness could be uploaded into vast, powerful, and incredibly durable computational structures. And what would a civilization of machines want or need? They wouldn't need a watery, temperate planet with a nice atmosphere. They might find the cold, efficient vacuum of space near a reliable energy source like a star or even a black hole to be a much more desirable home. Their thoughts might operate on timescales that are millions of times faster or millions of times slower than our own. We would be like mayflies, living for a single day, trying to comprehend the life of an ancient, slow-growing redwood forest. The difference in scale and substance would be so great that communication would be meaningless.
This idea also applies to their communication methods. We are listening for radio waves because that's what we understand and what we use. It's like a person on a deserted island sending smoke signals and assuming that anyone else out there must also be using smoke signals, completely unaware of the vast network of undersea fiber optic cables that carry terabytes of information around the world every second. An advanced civilization might have moved on to forms of communication that are far more efficient, far more subtle, and completely invisible to us. They might use tightly focused laser beams, which we would have to be in the direct path of to ever see. They might communicate using a modulated stream of ghostly neutrinos, which pass through almost everything. Or they might communicate using gravitational waves, sending ripples through the fabric of space-time itself. Or, most likely, they might use some form of physics that we haven't even begun to discover yet. It's entirely possible that we are living in the middle of a bustling, galaxy-spanning conversation right now, a constant hum of information exchange between ancient, post-biological civilizations. But we are simply, profoundly, and completely deaf to it. We don't have the right kind of ears to hear it. The great silence, in this quiet and humbling view, is not a property of the sky. It is a property of our own limited perception and our own infant technology. And now, for our final few paradoxes, let's return to the most mind-bending and philosophical ideas of all, the ones that question the very nature of reality itself. We have touched on them before, but they deserve their own quiet place in this grand tour of cosmic puzzles.
All right. We have journeyed through the strange labyrinths of time, the bizarre puzzles of the quantum world, and the quiet riddles of life in the cosmos. For our final ascent tonight, we will enter the highest and most abstract gallery of our museum. This is the realm of the ultimate questions, the paradoxes that touch upon the nature of reality itself. We begin at a familiar place, a quiet thought experiment that provides a simple and elegant, if deeply unsettling, solution to all cosmic paradoxes. This is the simulation argument. As we've discussed, this is a purely philosophical idea, but it has a powerful statistical logic to it. The argument, in its modern form, goes like this. First, you assume that it is physically possible for a consciousness to exist in a simulated reality, like a sophisticated computer program. Second, you assume that any civilization that reaches a high enough level of technological maturity will likely have the ability to create such simulations. And third, you assume that such a civilization would have a reason to run many such ancestor simulations, perhaps for research, or art, or entertainment. If you accept these three plausible assumptions, then a strange statistical conclusion seems to follow. There would, over time, be billions upon billions of simulated universes with conscious beings inside them, and only one base reality. Therefore, it is statistically far more likely that we are one of the vast number of simulated consciousnesses than that we are in the one original physical universe. This provides a clean, if deeply weird, solution to the Fermi paradox. The reason we don't see any aliens is because the programmers of our particular simulation simply never wrote them into the code. Perhaps creating one technological civilization was computationally expensive enough. Or perhaps the purpose of our simulation
is specifically to see how a civilization develops in complete and total isolation. The silence would be a deliberate feature of our simulated reality written into the program by its creators.
The simulation hypothesis is a perfect looping philosophical puzzle. It is completely unfalsifiable. There is no experiment we can perform, no observation we can make that could definitively prove we are not in a simulation. If scientists were to find evidence that our universe is made of discrete pixels at the smallest possible scale, the Planck length, this could be seen as evidence that we live in a computed reality. But it could also just be a fundamental property of the real universe. On the other hand, if we find no such evidence, it doesn't prove that our reality is real. It just means the simulation is very, very good, with an incredibly high resolution. It's a quiet, dizzying thought experiment that can feel a bit like the ground beneath your feet has suddenly become less solid. It's not a scientific theory in the traditional sense, but it is a powerful philosophical tool for questioning our most basic assumptions about what it means to be real. Now let's turn to another bizarre and deeply unsettling cosmological thought experiment. This is the paradox of Boltzmann brains. This idea, as we've touched on before, comes from thinking about the universe in its final state of heat death on a near-infinite timescale. In this cold, dark, and perfectly disordered soup, random quantum fluctuations will still occur, and if you wait long enough, any physically possible event will eventually happen. The paradox arises when you compare the statistical likelihood of two different events. Event A is the spontaneous fluctuation that creates our entire vast, low-entropy, highly ordered observable universe, which then evolves over 13.8 billion years to create you. Event B is the spontaneous fluctuation of a much smaller, simpler system, just a single, self-aware human brain, which exists for only a fraction of a second before dissolving back into the chaos. And this brain, in that fleeting moment, has a complete set of false memories of a life it never lived, and the perception of a universe that does not exist.
The deeply unnerving answer from a purely statistical point of view is that Event B, the creation of a single, momentary, disembodied conscious brain, is vastly, incomprehensibly more likely than Event A, the creation of an entire universe. So this leads to the quiet philosophical horror of the question, how do you know you are not a Boltzmann brain? How can you be certain that your past is real, that the world you perceive is real, and that you will continue to exist in the next moment? Now, this is not a theory that physicists actually believe. They see it as a reductio ad absurdum, an argument that shows there must be something wrong with our current cosmological models if they lead to such a bizarre conclusion. It suggests that our understanding of the relationship between entropy, time, and consciousness is still deeply flawed, but as a thought experiment, it is a powerful and quiet tool for contemplating the strange nature of our own existence. It is a paradox that uses the laws of physics themselves to question the reliability of our own minds. From these strange internal paradoxes, let's ascend one last time to the largest scale of all. This is the anthropic principle and its paradox of fine-tuning. As we know, the universe appears to be exquisitely and perhaps miraculously fine-tuned for the existence of life. The fundamental constants of physics, the strength of gravity, the mass of the proton, the energy of the vacuum, all seem to be set to values within a very narrow, very specific range that allows for a stable universe with stars, planets, chemistry, and conscious observers. If you were to change any of these values by even a tiny fraction, the universe would have been a sterile, lifeless place. So why is our universe so perfect? This is the paradox of fine-tuning. Is it an incredible, unbelievable coincidence that we just happen to emerge in a universe with the perfect winning lottery ticket?
The anthropic principle offers a quiet and slightly slippery answer to this puzzle. In its weak form, it is not really an explanation, but a statement of selection bias. It says that we should not be surprised to find ourselves living in a universe that is fine-tuned for life, because if the universe weren't fine-tuned for life, we wouldn't be here to be surprised about it. Our very existence as conscious observers filters out all the possible universes where observers can't exist. It's a simple, logical statement, but it can feel a little unsatisfying. A bit like saying, the reason the ground is the right distance from my feet is because if it weren't, I wouldn't be able to stand here. The strong version of the anthropic principle is much more speculative. It suggests that there is some underlying law of physics or some deeper principle that requires the universe to have the properties that allow for life and consciousness to emerge. In this view, our existence is not a coincidence, but a fundamental and necessary outcome of the cosmos. And as we've discussed, the anthropic principle provides a powerful argument for the existence of a multiverse. If there are an infinite number of bubble universes, each with its own random set of physical laws, then it is no longer surprising that we find ourselves in one of the rare universes that has the right combination for life. We have to be in such a universe because we couldn't exist anywhere else. The paradox of fine-tuning is, in this view, simply an illusion created by our limited perspective as inhabitants of one lucky universe among many. And this brings us to the final, quiet paradox of existence itself. We have explored all these strange and wonderful ideas, but how do we know any of them? This brings us back to the unreasonable effectiveness of mathematics, the paradox that our abstract human language of logic seems to so perfectly describe the deepest workings of the universe.
We have wandered through a labyrinth of thought tonight. We have explored the strange, looping corridors of time travel, from the classic grandfather paradox to the quiet, self-correcting nature of a consistent universe. We have descended into the bizarre and fuzzy world of quantum mechanics, where cats can be both alive and dead, and where our own observations seem to shape the past. And we have ascended to the highest, most abstract realms of philosophy, questioning the nature of our own reality, our identity, and our place in a silent cosmos. What is the thread that connects all of these strange and beautiful puzzles? For me, it is the quiet, mysterious, and deeply intuitive concept that we call time. Almost every one of these paradoxes, in some way, is a puzzle about the nature of time. The paradoxes of time travel question its direction. The paradoxes of quantum mechanics question its relationship with causality. And the great cosmological paradoxes question its beginning and its ultimate end. We feel time as a powerful, undeniable river, flowing always in one direction, from a fixed past through a fleeting present into an open future. This is the arrow of time. But why does it have a direction? Why can we remember the past but not the future? This simple, everyday experience is one of the deepest unsolved mysteries in all of physics. The leading scientific explanation for the arrow of time is the second law of thermodynamics. It is the law of entropy. It states that the total disorder of the universe always increases. A broken glass never spontaneously reassembles itself. The universe began in a state of incredible, low entropy order, and it has been moving towards a state of greater and greater disorder ever since. Our perception of time's flow is, in this view, just our perception of entropy increasing. The past is the low entropy state we remember, and the future is the higher entropy state we are heading towards. This connection between time and entropy is a powerful and elegant idea, but it doesn't solve the whole puzzle. It just pushes the question back one step further. Why did the universe begin in such a special, incredibly low entropy, highly ordered state in the first place? This is a quiet, fundamental mystery that our current cosmology does not have an answer for. And so we are left with the beautiful, quiet, and deeply human act of wondering. The paradoxes we have explored tonight are not flaws in the universe. They are flaws in our understanding. They are the beautiful, intricate knots in the tapestry of reality that show us where our knowledge is still incomplete. They are the gentle, persistent whispers from the cosmos that tell us there is always more to learn, always a deeper and stranger reality to be uncovered. There is a profound comfort, I think, in embracing these mysteries. The universe is not a simple puzzle that we are meant to solve completely. It is a vast and perhaps infinite landscape for our curiosity to wander through. The joy is not in finding all the answers, but in learning to ask better and more beautiful questions. So as you get ready to drift off to sleep tonight, let your mind be at peace with these quiet, looping, and wonderful puzzles. Let them be a gentle reminder that our common sense view of the world is just one small, limited perspective. The reality of time, of space, of our own consciousness is likely far stranger and more beautiful than we can currently imagine. And in that quiet acceptance of the unknown, in that gentle release of the need for simple answers, I hope you can find a deep sense of peace, a quiet sense of wonder, and a profoundly restful and dream-filled sleep.
Let's just quietly reflect for one last moment on the journey we've taken. We started with the classic human-scale paradox of a man and his grandfather, a simple story that reveals a fundamental knot in the logic of causality. We saw how the universe itself seems to have quiet defenses against such paradoxes, with principles of self-consistency that would make the gun jam or the car swerve, always preserving the integrity of the timeline. We then drifted into the even stranger idea of stories with no beginning, the Bootstrap Paradox, where a song or a watch can exist in a perfect, timeless loop, created by no one and existing forever. This quiet, strange idea challenges our need for a clear origin point, suggesting that causality can sometimes be a circle instead of a straight line. From there, we left the world of human intuition behind and descended into the quantum realm. We saw how a single particle can be in two places at once, and how our own act of looking seems to force reality to make a choice. We sat with a cat that was both alive and dead, a quiet, absurd, and profound illustration of the deep mystery of where the quantum world ends and our classical world begins. And we traveled back in time with a single photon, watching as our choice in the present seemed to rewrite its past, a quiet, mind-bending hint that time itself is not the simple, one-way street we perceive it to be. And finally, we ascended to the highest, most philosophical realms, pondering the strange effectiveness of our own mathematical thoughts, the fleeting nature of our own physical identity, and the great, silent, unanswered questions of cosmic origins and our place within it all. Each paradox has been a doorway into a deeper and stranger way of seeing the world.
The value of these thought experiments is not in finding a definitive solution. It is in the act of contemplation itself. By thinking about these quiet, impossible scenarios, we stretch the boundaries of our own imagination. We learn to be more comfortable with uncertainty, with ambiguity, and with the idea that our perception of reality is a fragile and limited thing. These paradoxes are a form of mental yoga. They are gentle exercises for the mind, allowing it to become more flexible, more open, and more at peace with the vastness of what we do not know. In our daily lives, we are often so focused on finding answers, on solving problems, on having a firm and certain grasp on the world. But there is a deep and quiet wisdom in letting go of that need for certainty. There is a peace in acknowledging that the universe is a labyrinth and that we are not expected to have a perfect map. Our job is simply to wander through it with a sense of curiosity and a sense of awe. Each paradox is a new, strange, and beautiful corridor in that labyrinth, and spending a quiet night wandering through them can be a profoundly relaxing and meditative experience. It's an invitation to let go of the small, noisy problems of the day, and instead to embrace the grand, quiet, and beautiful puzzles of existence. And in that embrace, the mind can finally become still. It can find its own quiet center in the midst of all this wonderful, beautiful confusion.
So, as we prepare for our final descent into sleep, let's take one last look back at the quiet gallery we have toured tonight. The ship of Theseus reminds us that our identity is a flowing river, not a static stone. Zeno's arrow reminds us that motion and time are infinitely more complex than they appear. The faint young sun paradox reminds us of the delicate, billion-year-long dance that has allowed our world to remain habitable. The black hole information paradox reminds us that our two greatest theories of the universe are still deeply and beautifully incomplete. The Fermi paradox reminds us of our profound and quiet solitude in a galaxy that should be full of conversation. And the quantum paradoxes remind us that the very fabric of reality, at its smallest scale, is a world of fuzzy, probabilistic magic that we may never fully comprehend. Each one is a quiet teacher. Each one is a small window into a larger and stranger reality. And the collection of all of them together paints a picture of a universe that is not a cold, dead machine, but a dynamic, surprising, and infinitely interesting place. It is a universe that is still filled with mystery, with wonder, and with the potential for endless discovery. And that is a profoundly hopeful thought. It means that there will always be new things to learn, new ideas to explore, and new quiet puzzles to contemplate on a sleepless night. The journey of understanding is an infinite one, and we have all the time in the world to explore it. So there is no need to rush. There is no need to have all the answers. All we need to do is to remain curious, to remain open, and to appreciate the beautiful, quiet mystery of it all.
And so we bring our long and winding journey
through the labyrinth of paradoxes to its final, quiet close. We have wrestled with the nature of time, with the strangeness of quantum reality, and with the deep philosophical questions of our own existence. We have seen how the simplest questions can often lead to the most profound and unsettling answers, and how the universe at every level, from the smallest particle to the grandest cosmic scale, is filled with beautiful, intricate puzzles. Let these strange and wonderful ideas now begin to soften and fade. Let the knots of logic gently untangle themselves in your mind. The questions will still be there tomorrow, patiently waiting. But for tonight, the exploration is over. It is time to let go of the need to understand and to simply rest in the quiet mystery of it all. Think of your own mind as a quiet, dark sky, and let these paradoxes be like distant, twinkling stars. You don't need to solve them or count them. You can just appreciate their gentle, mysterious light as you drift off. The universe is a vast and beautiful puzzle, and our own consciousness is the most beautiful puzzle of all. And in this quiet moment, all the paradoxes are resolved in the simple, peaceful state of letting go. It is time now to rest. Sweet dreams.